And this looks perfect. Do you have videos or audio?
No.
Perfect. And then my only last task is to just remind us that it's your presentation, 40-ish minutes, some discussion, Q&A, and feedback and summary from Carl.
Yep.
Good. I did not know you worked with Fernando. Uh,
Yeah.
I had no idea he was even in active inference, actually. Or
Yeah, I think he kind of works in some adjacent areas as well.
I guess he works in whatever he wants to. It's
Yeah.
fine. Yeah, exactly. All right. So once Carl is here, we can start. You're in Oxford now, currently?
Yes.
Yeah. So maybe I'll see you next week or this week even.
Oh,
Um,
yes, I forgot. Yeah. When are you
right.
coming?
Tomorrow I'm going to London, and then I think Saturday morning I'll probably go to Oxford.
Very nice.
Yes, and be around for a few days.
Yeah, meet up.
Yeah. Yeah. So if you're around, I'll uh, I'll come pester you.
Yeah, definitely.
And as you know, I've been looking forward to this.
Yeah, likewise.
You gave me a teaser trailer last time, but I
Mhm.
get to see you do a full concert.
Mhm.
Hey Dalton, hey Ed, hey Carrie, hi Stephen, and hi Sylvia. And did I see Yachi here as well? Or did Yachi change their name to Sylvia, maybe? It's nice to have so many guests present. And I am, yes, everything looks good. So once Carl is here, we can start.
Okay. Can you hear me okay?
Say again?
Can you hear me okay?
Yeah, somewhat camera affected sound, but or not camera, microphone affected sound, but I think it'll be
Is that better?
much better.
Okay, cool.
Thank you. Hey Ryan, welcome. And Carl is here. Hey Carl, hope you're doing well.
I am, thank you. Thank you.
Okay.
Thank-
Uh,
So then I think we are ready for today's presentation. It is, as always, a huge pleasure to bid you welcome, David. And today, David will talk about a model of attention using active inference, and as I understand it, some version of drift diffusion modeling together, which is exciting.
Yep.
We'll do your presentation, then we'll do Q&A, and Carl will summarize. Stage is yours.
Yeah, so hello, thank you for all for being here. I'm going to be presenting active attentional inference for multi-attribute choice under uncertainty. And this is ongoing work with my collaborators, Sarit Kraus, Fernando Rosas, and Michael Waldridge. So to begin with some motivation, Herbert Simon once wrote that a wealth of information creates a poverty of attention and a need to allocate that attention efficiently among the overabundance of information sources that might consume it. Now, in the modern world filled with endless sources of information that are optimized to capture our attention, how do we actually manage this allocation of attention to the places that really matter in our lives? And moreover, in an increasingly algorithmically mediated society, which is optimized to capture our attention, it's really important to understand what exactly it is that drives this capture so we can figure out ways to reclaim control of our attention. And later on, Michael Gratiano wrote that if you could know one thing about an animal to best predict its behavior, I suggest that attentional state would be the wisest choice. If you could know what the animal is attending to, how much of its attention is allocated to the item, and what the consequences of attention are, then you would gain considerable ability to predict the animal's behavior. And now what he was getting at here is that what we pay attention to is deeply tied to the decisions that we make. And this is what motivates formalizing the relationship between attention and choice, and also understanding exactly what drives our attention in the first place. So just to begin with a motivating example, I'm going to present to you two phones, and I'd like you to come to a decision on which phone you would prefer to have. So here are the phones, and I'll just give you a few seconds to make up your mind. Now, if we just take a moment to reflect on what just occurred as I presented these phones to you, a bunch of information suddenly appeared on the screen, and you had to very quickly, in a few seconds, make sense of that information, weigh up all the different features of these phones, and then arrive at some decision about overall, which phone you would prefer. And essentially what this work is exploring is how this process occurs and what are the factors that contribute to it. So for a quick overview of what I'm going to be talking about, I'll first start by presenting the basic structure of the generative model for multi-attribute choice with structured hidden states. Then I'm going to talk about policy selection. So how does an agent actually decide what to look at or what to pay attention to, and then ultimately which item to choose. I'm going to frame this in terms of expected free energy minimization. Then I'm going to present a process theory for how this might work using a model-based evidence accumulation model with active inference. And then I'm going to present some empirical results where we fit different variants of this model to two real human choice data sets, which are the reversal bandit and consumer choice data sets. And the key guiding question here is how do we choose between options that differ across multiple uncertain attributes when information must be sampled sequentially? And so now why are we interested in this particular multi-attribute choice under uncertainty model? Well, the first thing to notice is that in most real-world choices, we can think of them as involving multiple options across multiple attributes. And now the question is, if we have all of these different attributes, how do we combine them, the preferences of these distinct features into a single choice? And now attributes are often uncertain, so that means that deliberation is an information sampling problem. And importantly, attention changes which evidence is sampled and which option gets amplified in our choice. So if you imagine here, we have these two phones that I showed you earlier. When I first presented them to you, you didn't immediately know what all the different values were, and you had to fixate on them in order to resolve uncertainty. And this is something we're going to try and capture in our model. So now some key empirical phenomena that we'd like our model to fit and include. So first of all, there are attentional effects, where gaze duration causally biases evidence accumulation, which means that when I'm fixating on an option, it accumulates evidence for being the best alternative more quickly. We've also observed that active sensing via eye movements shapes belief formation in both lab and real-world settings. And also, we know that high-value stimuli capture attention automatically, even when they're not necessarily rewarded. Now, on the other hand, there are many papers understanding exploration or exploitation effects in human choice and attention. And so what we've seen is that within a trial, attention shifts from uncertainty reduction early on in a trial to value exploitation later on in an episode. And it's also been demonstrated that information seeking drives attentional capture independently of value. And as we'll see later, there have been experiments to show that humans balance between exploration and exploitation. And this balance is fundamentally driven by belief state uncertainty. So now we get to the basic model that we're going to be using throughout. And we're going to start by assuming that the agent chooses between n alternatives, each having m features. And each of these features is going to have some hidden states from a set of possible hidden states. We're going to use j indices to denote the features and I indices to denote alternatives. And we're going to assume for now that everything is discrete, but you can easily imagine extensions into the continuous setting. And so basically, we're going to think about the generative model as factorizing by maintaining independent posterior beliefs per alternative and feature pair. And these state spaces are going to be heterogeneous. So for example, feature 1 might have 5 levels, whereas feature 2 might only have 2. And the agent is going to sample potentially noisy observations of these hidden states. So now belief updating is going to work in a sort of hierarchical fashion where we have within trial beliefs and between choice beliefs. And so within trial beliefs track the beliefs of the agents as a single decision is being made in real time. And these beliefs can be updated based on the information that the agent samples using their attention. And in contrast, these between choice observations and beliefs are referring to the observations that are made about an alternative after actually choosing that alternative. So like, for example, suppose I'm choosing between different ice creams. I'm not going to be able to learn what the tastiness of a particular ice cream is, just by looking at it. Though I may, resolve some uncertainty because I see it has a certain flavor, and I know, which flavors I like. But when I actually buy an ice cream and eat it, I also get to experience the tastiness of that ice cream more directly. And that's what this between choice observation essentially is. And so for this reason, we're going to distinguish between these beliefs and observations within a trial, and those are governed by attention, and beliefs and observations between trials that are governed by our experiences of the consequences of our choices. And so for now, we're just going to be assuming that the agent in our model performs a Bayesian belief update. I know maybe this is a bit of a sin in this area of research, but you can easily imagine relaxations to variational belief updating. And so yeah, as I mentioned, within a trial, each fixation is going to sample an observation, and Bayesian inference is then going to be performed for the sampled alternative feature pair. And in contrast, between trial observations are only made for the chosen alternative, and the between trial beliefs are updated based on this chosen alternative only. So now just to come back to our phone example, when you fixate on, let's say, the battery feature of phone B, your initial beliefs, which were probably pretty uncertain, sharpened after you looked at the battery capacity. And so what happened essentially was that you had a likelihood function that was very precise, which allowed you to update your beliefs directly to the correct value of the battery state of phone B. So now we're going to move on to where preferences come in. And we're going to assume that we have per feature value functions, which are related to the pragmatic value term in active inference. And these are going to be denoted by Vj, which map from states Sj to the real numbers. Then, given our beliefs about the underlying states of each feature alternative pair, we can compute an expected value under these beliefs. And so if I'm very uncertain about the hidden state, then my expected value is just the average of my value function over that feature. Whereas if I'm very certain about what the hidden state is, then my expected value is just the value for that particular feature state. And so in active inference terms, we can think of value as encoding the preference prior, which is a C matrix and can be learned from experience. And yeah, as I mentioned before, each feature has its own value function, which can be thought of as a C matrix decomposing across different features. And these values may be learned, for example, through reinforcement learning, or they could be inferred via, for example, variational Bayesian inference. And there are several studies in the literature showing that humans and other animals have these kinds of decomposed preferences over features. Okay, so now let's move on to the overall evidence accumulation loop. So just for some background, evidence accumulation models are this sort of class of models that have been very popular over the last several decades, particularly in the decision neuroscience and cognitive science literatures, for being able to quite accurately predict not just what people would choose, but also how long they'll take to choose. And they can be used to explain many violations of the classical axioms of rationality that humans tend to exhibit. And so our version of the loop begins with computing these pragmatic and anesthetic values. And we're going to see how all of these steps work in subsequent slides, but I'm just going to give you a high-level overview here first. And so from these pragmatic and anesthetic values, we'll compute the drift and attention signals. And then from these, we're going to update the attention distribution, which is basically a distribution that represents the probability of fixating on each alternative feature pair in the next time step. Then we're going to sample a fixation from this distribution, and then the agent is going to make an observation and update their beliefs. Then we're going to use that sampled fixation to update our evidence accumulators, which are essentially stochastic processes that you can think of as representing the sort of evidence for the hypothesis that each alternative is the best one to choose. And then we essentially check these evidence values against some threshold. And if one of the evidence values exceeds that threshold, then we pick that alternative. And if not, then we just keep on repeating this loop until a choice is made. And so some key equations guiding this. As I mentioned before, the drift signal is computed as a sum of a pragmatic and epistemic value term. And so here the pragmatic term is just the expected value of feature j of alternative I at time t. And the epistemic value is a constant lambda b times the expected information gain for feature j of alternative I. And crucially, we'll see later that this is operating on the between choice beliefs. Now, in contrast, the attention signal, which is denoted as ji, will be composed of the accumulated evidence so far, plus another constant lambda w times the expected information gain, where this information gain is based on the within trial beliefs that we saw earlier. And then notice that for the attention signal, we're using this accumulated evidence term instead of the expected value. And this can be thought of as a running estimate of the overall pragmatic and epistemic value of a particular alternative relative to the other ones. And lastly, we have the attention update equation, which is based on this attention signal. And this is the solution to a regularized optimization problem, which is given by a tilted Boltzmann distribution with a parameter tau. And so we're going to unpack these equations in subsequent slides. So yeah, I probably don't have to spend too much time on this slide, but just so that we're all on the same page. One of the most important concepts that we are contributing to this literature on evidence accumulation models is that of expected information gain. And so essentially, this represents the expected degree to which one would reduce their uncertainty about the hidden state of a particular variable from before making an observation to after making one. So you can see in this figure, if you have a very uncertain prior and then an observation helps you to resolve that uncertainty, then you have high information gain. And the expected information gain is just the expectation taken over your marginal likelihood. And so in active inference, this is known as the epistemic value, and it captures the idea that not all information is equally useful. Yeah, and so as I mentioned before, expected information gain measures how much an observation is expected to reduce uncertainty about a future state. And we use these expected info gain terms, which I'll just call EIGs, corresponding to those for our within trial beliefs and between trial beliefs. And so mathematically, the expected information gain is the expectation under the marginal likelihood of the KL divergence between our posterior after seeing the observation and our prior before seeing the observation. And what's been shown in the literature is that attention is drawn to information where beliefs are most uncertain and observations are most distinguishing. So now, coming back to the drift and attention signals, we'll recall that the drift signal is computed as the sum of expected value plus a parameter lambda b times the EIG for between trial observations. So the idea here is that the evidence I accumulate for an alternative is related to how much value I think it might give me, but also how much information it might give me. So for example, if I see an ice cream flavor that I've never tried before, I might be curious to try it to see whether I like it. And this is what's contributing to the actual drift. Now, the attention signal is based on the sum of the accumulated evidence up to the current time point, plus another parameter lambda w times the EIG for within trial observations. And so, attention is driven by my current estimate of which alternative I think is best, and what information I might acquire by attending to different alternatives. And the key distinction here is that looking and trying are distinct epistemic policies. And so evidence accumulation is related here to expected value, while attention is related to accumulated evidence. But they both have this epistemic component. And just to relate this to the standard expected free energy decomposition, we can think of the expected free energy as the negative of the sum of the pragmatic and epistemic values. And here, for example, if we set lambda to 0, then we just have pure exploitation, which means that the agent essentially is going to ignore uncertainty. Now, if we had some non-negative values of lambda that are some sort of intermediate values, then there will be this kind of balance between exploration and exploitation. Whereas if we had a really, really large lambda parameter, then the agent is mostly going to focus on exploration. And so, yeah, we can think of lambda as being analogous to this inverse precision of the preference prior in active inference. Okay, so now we come to the attention mechanism, and this is going to guide how attention is updated within a trial. And we're going to formulate it as a solution to an optimization problem, which is essentially the sum of the attention probabilities times the attention signals minus the constant tau times the KL divergence between the attention distribution that we're trying to find and the prior attention distribution. And so this optimization problem has a nice closed form solution, which is essentially a tilted Boltzmann distribution over these attention signals. And it's going to be weighted by their previous attention distribution. And intuitively, this captures the idea that attention has inertia. So deviating from the prior is costly. And this is a well-documented phenomenon in the empirical literature. Now, we're going to model inertia by assuming that there is a cost of shifting attention away from the prior, which is measured using the KL divergence. So, when this parameter tau is low, then attention tracks the signal S closely. And when tau is high, that means that the cost of shifting attention is high, so attention stays near the prior, and it is basically governed by habit or inertia. And here, the prior is, just the previous attention distribution. Okay, so now we finally move on to the actual evidence accumulation process. And this is going to start off by computing a quantity UI bar, which just aggregates the utilities of each feature for this particular alternative that we're considering. But crucially, it's going to be weighted by a gaze discount. And so the idea is that if you're fixating on a particular feature, then you're going to accumulate evidence for that feature more quickly. Whereas if a feature is not fixated, then it's going to accumulate evidence more slowly. Then for alternatives, we have a similar story where the fixated alternative accumulates evidence more quickly than non-fixated alternatives. And these are both phenomena that have been demonstrated in the empirical literature. And then finally, we get to this evidence update equation, which essentially takes the previous evidence value and then adds a term, which is this gaze-weighted drift, UI tilde, plus another term, which is, I guess, optional. And this essentially corresponds to a leak inhibition term. This term comes from a model known as the leaky competing accumulator model, which is one of the most canonical evidence accumulation models in the literature. And then we also add some Gaussian noise to reflect some random variation in the process. And so the key idea here is that gaze modulates attention. So these gaze discounts, gamma F and gamma A, you can think of them as precision modulation, where attended channels for evidence accumulation have higher gain. And the fixated feature and alternative pair accumulates more evidence than non-fixated ones. But nonetheless, evidence accumulates in parallel for all alternatives at each time step. It's just that the ones that are not fixated get discounted. Okay, so just to show you a quick demonstration of an example of an evidence accumulation. So simulation of our model on a real trial that was presented to a participant. On the top here, we have the actual evidence values for two different phones evolving as fixations occur until the evidence for one of the phones hits this threshold. And here we're showing a relative threshold, which is just calculated as the mean evidence plus some constant, which modulates essentially how confident the decision maker needs to be before making a final decision. And then on the bottom here, we have just an illustration of how the attention distribution over features evolves as the trial proceeds. which is based on this attention signal. And you can see this kind of smooth behavior that's created by the KL regularization. Okay, so that's the model. Now, we have this model. How are we going to fit it to some data? So, one approach that I initially explored was just to use a simulation-based likelihood where we take a trial observation, such as fixation proportions and the choice. And then we can estimate the likelihood of this observation given certain parameters by running a bunch of Monte Carlo simulations of our model, and then summing a kernel density estimate, which essentially measures the similarity between observed and simulated trials. Then we can just take the average of this value to approximate the trial likelihood. Then from these, we can compute a log likelihood over all trials as just the sum of these individual trial log likelihoods, assuming that they're independent. And then we can optimize the parameters to best fit the data using some derivative-free search method. And so crucially, this has to be simulation-based because our model is just a simulator. There's no closed-form solution for the likelihood, unfortunately. So it's just a stochastic simulator. And using Monte Carlo estimation means that we have to run the simulation many times per parameter setting just to get reasonable estimates. And this is extremely expensive per evaluation. Yeah, and many simulations are needed to do this, and you have to run this for every participant, making it extremely slow. And so this motivates a relatively new approach called neural likelihood estimation. And the idea here is essentially we're going to take a neural network and use it to approximate the likelihood function, and then perform maximum likelihood estimation using the neural network as a surrogate model. So we're going to be using a technique known as mixed neural likelihood estimation. And the basic way that it works is that we start by sampling a bunch of parameters of our model, our simulator model, from some prior distribution, which is usually just a uniform distribution. And then we're going to take these sampled parameters and then simulate our model to generate a bunch of samples from the likelihood function of our model. And we're going to do this many times. Then that gives us a data set. And so what we can do is we can train a neural network to approximate the likelihood function, so the mapping from parameters to observed outcomes. And we can just use standard stochastic gradient descent here. Then after this, we have a neural network that we hope approximates the true likelihood reasonably well. And so then what we can do is when we want to fit our model to a particular participant, if let's say we want to find a maximum likelihood estimate of the parameters that best explain the data, we can simply perform gradient descent on the likelihood with respect to the input parameters to find a maximum likelihood estimator. And here we keep the weights of the network frozen. So yeah, we can compute this gradient because the neural network is inherently differentiable. So why might we want to use MNLE? Well, the first thing to notice is that MNLE learns a trial level neural likelihood from simulations. And crucially, this handles mixed data, which in our case, as we'll see later, consists of continuous fixation, proportions, and discrete choice. And the advantage of using this approach is that we just need to train the neural network once, and then we can reuse it for all participants by optimizing the neural log likelihood with each participant's actual data. So this is much quicker than having to generate a bunch of simulations for each participant separately. And yeah, it turns out that this approach is orders of magnitude faster than direct Monte Carlo simulation. Okay, so now we're going to get to some of the results. These are relatively preliminary results. We studied 2 human choice data sets. In the first data set, we are going to compare our model to one proposed by the authors. And so essentially in each trial of this task, participants can decide between choosing a square or a triangle. And one of these shapes is designated as a lucrative shape, and it would return a reward of +1 with a probability of 85% and a reward of -1 with a probability of 15%. And the detrimental shape, the non-lucrative shape, will return a reward of 1 with probability 15% and a reward of -1 with probability 85%. So these probabilities are essentially flipped. And these shapes are also overlaid on backgrounds of different colors. And the color of the background would indicate whether the choice would be informative or non-informative. So an informative choice means that the reward that is obtained by making that choice is revealed after the choice is made, whereas a non-informative choice means that you wouldn't know what the reward was that you got. So there were 24 participants in this study, and there were 2 runs of 80 trials each. Essentially, you can think of this as a 2-armed bandit with independent reward and information dimensions. And interestingly, essentially at 3 different points during these 80 trials, the shape that's lucrative would reverse unpredictably. So essentially, the agent is incentivized to continue exploring throughout the episode by selecting the informative shape. They were informed that the shapes would reverse at 3 points during the trials, but they weren't informed when this would happen. And so, yeah, we fitted our model to this data, and here we just use 2 free parameters, which is the threshold for decision and this EIG weight lambda b, and here we're using it in a convex combination. Also, some other things to note. These conditions were randomized, so sometimes the lucrative shape would be informative in this sort of congruent fashion, and other times there would be conflict where the lucrative shape would be non-informative. And so these conflict trials in particular were the ones that really kind of introduced this trade-off between exploration and exploitation. Okay, so yeah, here are results. So we compared our model to the best one that they proposed, and we fitted this directly. So we didn't use the neural likelihood estimation for this one because it's a relatively simple model. And their best model essentially what it does is it samples a choice directly from a softmax distribution of a convex combination of the expected value and expected information gain. And yeah, so remember our model computes this choice by representing the drift. And we use this convex combination of expected value and expected information gain in the drift, but we run this accumulation process until a choice is made. And so our model had a lower BIC than theirs on 22 out of 24 participants. And the protected exceedance probability was virtually 1. Both models achieved roughly 87% choice prediction accuracy. But the key insight here is that replacing the standard softmax with our evidence accumulation better captures this trial-by-trial variability between participants. Yeah, so now while this data set that we just saw with Horvath showed that evidence accumulation models with information gain can better fit the data than a standard softmax sampling model, we'd also like to understand how the full model with attention across different attributes works in a real-world data set. So that previous one only essentially had one real feature and couldn't really test multi-attribute attention, and they didn't capture that data. And so we really needed a richer data set. And unfortunately, we found this one from Glius and colleagues, where they essentially presented participants with these phones, from the example that you saw earlier. And crucially, they also tracked their eyes as they were deliberating about which phone they would prefer. So in this data set, there were 63 participants, and their eyes were tracked as they were deliberating. They chose between 2 smartphones, which had features of display, battery, and memory. And each participant chose between 120 different pairs of phones using different difficulty levels, which were obtained by essentially taking prior ratings of different phones to create new options that would be more or less difficult to choose between. And these feature positions were randomized across trials to eliminate any spatial effects for attention. And observations were in our model fitting were choice, fixation proportions, and the number of fixations, which is essentially a proxy for the reaction time. Okay, so essentially, because our model has lots of these different choices and components, what we're interested in here is conducting an architectural comparison, essentially to determine what choices of different parts of the model best explain the data. And so here we looked at 4 different architectural components. So we had the drift mode, the attention signal, the threshold, and the attention prior. So for the drift mode, we compared 3 different variants. So 2 variants of the leaky computing accumulator model. And then we also had one which had a local drift that didn't feature any leak or inhibition. Then for the attention signal, we looked at an evidence-based signal versus one that uses the expected value. For the threshold, we considered a relative threshold, which is the one I showed earlier in the example, versus an absolute threshold, which just stays constant during the episode. And then for the attention prior, we either regularized to the previous time steps attention distribution or to the initial distribution, which is essentially similar to an entropy regularizer. And so we tested these 4 dimensions, and across attention signal, threshold type, and attention prior, there was very strong evidence that the evidence-driven attention, the relative threshold, and the previous attention prior were the ones that were the best choices, whereas for the drift mode, it was inconclusive as to which one was the best. So 3 of them showed decisive evidence, and the other one was ambiguous. And so for this one, we used the mixed neural likelihood estimation procedure that I showed you earlier. And here I've also just plotted some violin plots, essentially showing the per participant difference in BIC between the best model and the second best variant across these different architectural choices. And here we see that evidence-driven attention, relative threshold, and previous prior clearly worked best for the large majority of participants, whereas we can't really say for the drift mode. So also one thing to note here is that there are several outlier participants here. You can essentially kind of ignore these because those trials, for those participants, many of the trials were missing some fixation data, and so the model just fitted them really unreliably. Okay, so that's it for our model. Just to summarize, so we argue that multi-attribute choice needs a model of search under uncertainty and not just final value comparison. We propose a model that integrates beliefs, information sampling, and attention into classic evidence accumulation models of value-based choice. And finally, I think it's really important to emphasize that understanding what drives our decision making is important if we want to promote better decisions and prevent unwanted manipulation. And for some future work, natural empirical extension would be to use our model to predict actual fixation sequences, not just proportions. We might want to collect richer data sets for multi-attribute, multi-alternative choice. And we might also include both pre and post-decision EIG to really disentangle these effects. Another interesting area to explore would be value learning, where we essentially incorporate value learning into the model to capture how preferences evolve across different trials. For modeling extensions, there are a number of different ones that we could look at. So one natural one would be using hierarchical generative models, where we might have a group level prior over the parameters. As I mentioned earlier, we could incorporate variational inference to relax the Bayesian inference assumption for more realistic belief updates. And we could also include dynamic environments where choices actually affect state transitions in the full sort of POMDP setting in active inference. And finally, just as sort of more applied extension, we might think about decision supports that essentially use our fitted attention model to design interfaces that mitigate manipulation and promote healthy reasoned choices. So that's it, and thank you for your attention.
Thank you, David, for a wonderful presentation. Let's all, as is the custom, unmute our microphones and give David a round of applause. All right, that was riveting, and as a modeler, always a huge pleasure to see some modeling work presented. Now we'll go into Q&A, comments and questions in general. I'll keep an eye on the chat, and anyone can raise their hand if they want to ask or comment something. But maybe, and I have a lot of things that would be fun to talk about, but in order to stem that barrage of questions from me and maybe others, maybe a good starting question to just frame the discussion is how you think this could be the most useful for you. So do you want feedback on the modeling, on future work? Do you want to talk about
I
your
think,
data?
yeah, really any feedback. I'm admittedly not a modeler. I'm a computer scientist, and so I really don't have a background in this, and this is kind of also a way to kind of learn how all of this works. So yeah, particularly on the modeling side, how to strengthen those empirical results, and also just more fundamental questions around like different choices of different components of the model, questioning things or providing different sources or references to literature that may inform how we go forward with it. And also, yeah, any applications or ideas for what might be good uses of this model would also be great.
All right, perfect. Then anyone raise their hand if you have questions or comments. I can maybe start with just a small one. Let's see. Yeah, I just wanted to mention, so you're using this simulation-based synthetic likelihood model. So just completely technically speaking on the fitting side, which is, by the way, very exciting and something I wanted to learn myself for these models where you don't have a clean likelihood otherwise. I just wanted to note that I know that once you have that synthetic likelihood, you could use it with MCMC or variational inference to get a full posterior instead of just the maximum likelihood estimate.
Yeah.
Which might be nice and also allow for better model comparison metrics than the BIC, which is of course simple.
Yeah.
Just
Yeah.
want and I
Yeah, I
know,
think that makes a lot of sense.
so I mean, mostly I'm saying this because it's something I want to learn myself. I also know that there's stuff they call normalizing flows,
Yeah.
where we train the neural network to approximate the posterior directly instead of approximating the likelihood, and do it in a way where you get a full distribution out. So since
Yeah.
you're anyways in the game of SBI, of simulation-based inference, well, one
Yes.
might take it all the way and do full Bayesian inference instead of MLE. But that's just a technical note. I don't know.
Yeah, yeah. Yeah, so I think I also saw this in the SBI literature. They call this neural posterior estimation.
Yeah,
Yeah, I think that's definitely something that might be more rigorous. But it seems like the NLE approach was kind of the first quick, easy way to get a handle on these things.
I know. Yeah, I mostly wanted to flag it.
Yeah, thank you.
Is given that we're trying to be Bayesian all over the place, we might as well be doing our model fitting as well.
Yeah, yeah, makes sense.
And might I ask you just briefly, did you implement this in Python, in
Yes,
MATLAB,
Python.
with some kind of JAX implementation, or do you
No, just PyTorch.
PyTorch? Okay, same. All right. And like I said, I'll keep my eyes on any raised hands or chats. And in the meantime, I'll bombard David. So another question or thought, especially since you're in an active inference crowd, is that sometimes people distinguish attention from salience. And of course, terminologies differ, but at least in the active inference literature, I've seen that used to distinguish salience as, if I'm not mistaken, as essentially what information that would be the most useful to sample. so where it would be most useful to attend, or
Mhm.
to move my gaze, and then as distinct from just the precision, expected precision on the input that decides how much a given input will update my beliefs.
Mm.
If I'm not mistaken, the second one is usually called attention, but I think you're modeling specifically the first of the two, like where to sample data from, basically.
Yes. Yes. Yeah.
So at least in the context of active inference, that's probably terminologically speaking nice to be
Right.
clear.
Sure. Yeah.
But I think even in the non-active inference world, they have all sorts of names for these things, right? I have covert and overt attention, I've heard
Mhm.
called as well.
Yeah.
And
Um, yeah. So I think in some of the sort of decision sciences literature, they typically use a salience to refer to properties of the alternatives. That's sort of, like something is salient if it jumps out at you more, if it's like brighter or more colorful, something like that. And so I didn't want to confuse uh,
yeah.
those people. But yeah, I agree that yeah, these terminologies are all used in different ways.
So that's probably a call for just being completely clear in the beginning.
Yes.
Which
Yeah.
which makes sense. Like I was wondering, like, is he going to model where people look or which part of the input that they have higher precision on? And in this case, it was the
Right.
where people
Yeah.
look.
Yeah.
Right. Ryan has a question or comment.
Mhm.
Hey, thank you so much for the presentation. It sounded really, really interesting. So I have something more of a clarifying question. So in your leaky model, is the leakage rate a fixed constant, or is it something like the system can infer and adjust? Like if we assume more volatility in the environment, would the model kind of benefit from a flexible leak where it kind of washes out old evidence accumulation?
Yeah, so this leak parameter, I can show you the equation for it. So we have two parameters. One is for the leak and one is for the inhibition. And the leak is basically just a decay over time. And so we have this parameter kappa that we're fitting for the data. This leak parameter is a constant, so it's just the leak is just dependent on the previous evidence value. Yeah, I think it's definitely an interesting question. What if we had a dynamic leak? But typically, the LCA model assumes that these are just constants that multiply these leak and inhibition terms. Um, yeah, I think there's an interesting connection here to memory, or maybe short-term memory or something like that. Where if you have really poor short-term memory, then you can think of that as like the leak being very high. And then, yeah, also related to volatile environments, if information quickly becomes redundant, or if the environment is shifting very quickly, then you might not want to weight previous evidence too heavily, and so you might want to have a higher leak. But yeah, I think this is all interesting direction. I don't know of any work exploring this in more detail.
Great, thank you.
And we have a comment from Sylvia. She says, or they say, you mentioned implications for making healthy and reasoned decisions. I was wondering in this context how you would define what counts as adaptive or rational versus not. I'm asking because many cognitive biases may not be inherently maladaptive in themselves, even though they are seen as biases. This is right down your alley, I think, David.
Yeah, this is a great question. So this is actually related to a lot of the work that I've been doing on bounded rationality. And essentially the idea there is that people aren't just optimizing an expected value or reward function, but they actually have to optimize this trade-off between achieving your preferences and the cost of achieving those preferences. And these costs can be formulated in terms of the energetic costs to actually like achieving your goal, but it can also be the cost of changing your mind and your policy, finding a good policy to achieve your goal. And so there can be cases, for example, if you're playing chess, you can't simulate all the possible moves and then figure out what the optimal move is. There is a cost for doing each rollout in your head. And so what you're actually trying to find is an optimal trade-off between the goal achievement and the cost of information processing. And this is sort of broadly known in literature as resource rationality models. And these models essentially say that, a lot of the apparent biases, exactly as you mentioned, Sylvia, are actually the result of potentially, an optimal trade-off between costs and benefits. So I would say that that is probably a better way to think about, what might be a good or a healthy reasoned decision. We don't want the person to just, reason forever and get stuck in this kind of, paralysis by analysis. There are time constraints, there are resource constraints, there are opportunity costs. And so actually what we want to find is this kind of sweet spot or optimal trade-offs.
Jesus, thank you. Which I suppose David needs a good model of the cost of thinking, right? Which is
Yes.
an interesting research program.
Yeah.
All right. I have another question, unless someone else is there. It's just so maybe I wanted to just acknowledge that. So I'm also cognitive modeler, and I usually use these Bayesian mind models, and many of them are trial by trial models. So you get an input and you update, and you get another input and you update. And something very interesting to me is to extend those models to include the time course of the updating between trials. And
Mhm.
I see something like the work you're doing is kind of adjacent to that, at least, if not. Because that's exactly what the drift diffusion and evidence accumulation models in general try to do, right? They get at the time course of making a decision or getting to my belief that I act on and so on. So with that in mind, uh, one thought was, since you're just discussing the leak here as being, you could have a better or worse, or a given leak parameter value could be more or less adaptive depending on how volatile the environment is, for example.
Mm.
So I'm wondering in general, and maybe I'm just asking your thoughts on this, if you could, how one could rethink these models directly as Bayesian inference. So in this case, I suppose the leak should be, in a Bayesian model, you automatically get forgetting quicker in volatile environments because having highly volatile environment in your generative model will lead to your priors becoming less certain quickly and therefore being updated more when you get information.
Mm.
So you kind of get this leak
Right.
automatically. Do you think we could, open question, but do you think we could reformulate something like an LCA to be an actual Bayesian process?
Mm.
Do you have thoughts on that? Maybe is my open question here.
Yeah, that's really interesting. I hadn't considered that before, but I definitely think that there's something to it. This LCA model was kind of inspired by, yeah, like different phenomena that we see in the brain, like neural action potentials leak over time, and there is mutual inhibition between different neural populations in representing evidence for choices. But then these kinds of parts of the equation were just like added to it without a more principled derivation. So I think that there definitely would be some way to formulate it in a Bayesian framework. I don't have immediate thoughts about how that might look, but I definitely think that's worth considering.
Yeah. It's because you've touched both of them now quite
Yeah.
like you spent some time with them. So yeah, okay. All right. We see a comment from Ryan saying possibly incorporating a Dirichlet distribution would transform the model from a simple choice and latency accumulator into a Bayesian hierarchical model that handles multiple categories or states of the environment. Do you want to expand a bit on that, Ryan? Or do you already, David, completely understand Ryan's meaning here, which
Um, yeah, so yeah, maybe could you expand on that, Ryan? I'm not exactly clear what the Dirichlet distribution is over here.
or how it's incorporated, I guess is my question. Yeah.
Yeah, sorry. So I was thinking this was kind of a follow-up on the last comment. Just if you were to have something like three-armed or four-armed bandit, then you could start to have the Dirichlet distribution to allow like this maintenance over the probability distribution of all of the arms, which is currently the best. Um, and so you could have something like a more Bayesian formulation then, where you could have categorical likelihoods, um, since the choice itself is categorical. Um, yeah, I
Yeah.
could maybe expand further, but yeah.
Yeah. So in the original way that I was thinking about this model, I was using Dirichlet distributions to update the beliefs. But yeah, I guess like when it comes to fitting the model to different settings, you may not necessarily be, getting new evidence uh, after each choice, especially if the trials are independent. So I think, yeah, definitely depends on the situation that you're modeling. But yeah, I think using Dirichlet distributions is a very natural way to do it.
I have two more questions, David, if you're not tired of me yet.
No, no, no.
Um, so one is that if I understood you correctly, when you look at a given option,
Mhm.
the evidence for picking that option goes up, and then it goes slower up for the other options. Is that right?
So not necessarily. It depends on the drift signal that's computed.
Yeah.
Let me just find that. Yeah. So essentially, yeah, this drift signal takes in this, where is the drift signal? This pragmatic plus epistemic value term.
Hmm.
So that could be negative if let's say the alternative is really bad.
I see.
And then it does this feature weighting, feature an alternative case weighting procedure, and then it adds that to the evidence. So if I'm looking at something and it's, like a really bad outcome, then it's actually going to decrement the evidence. But the gaze weighting means that whatever is happening to the evidence is going to happen faster than the other ones that are not fixated. And then you have these other leak inhibition and those terms potentially.
So staying a little bit at this Bayesian reformulation of this, I suppose you would, if you had an agent that received an observation of each of them at the same time on every fixation point, but where it's highly noisy, or it's expected to be highly noisy, everywhere it doesn't look,
Mm.
you would get the same dynamics. Do you think?
Ah, that's interesting. I'm not sure if it would be the same dynamic, but I think that's definitely another alternative way to formulate it.
Because then
Um,
if you get noise observations, no matter what they point towards, you would update slower.
yes, yeah,
And update faster where you fixate just because let's say, the
right,
expected quality of the observations is higher.
right. Yeah, so you could maybe formulate it so that the gaze weighting is a function of how noisy or how sharp your observations are. So if an observation is very noisy, then you essentially would discount that heavily in your evidence accumulation.
Yeah. In your
Yeah.
update. Yeah.
Yeah, so these gamma parameters are just, constants for now. But yeah, you can also exactly imagine computing them in a Bayesian setting.
I mean, you could have let's say you receive whatever, you could have a fixed precision for everything you don't look at, and a different fixed precision for the thing you look at, and you might get exactly
Yeah.
something like this.
hmm Yeah.
And so relatedly, so I'm where I'm kind of spending all my questions asking like, why didn't you go fully Bayesian on this? But that's my own bias as a Bayesian mind modeler, right? So don't feel pressure to that. But you basically look something very analogous to an expected free energy, maybe even formally equivalent to it in in some situations, or in this situation, as your not your drift. Well, I guess both signals, right? If I understand right. And one is the so
Expected value is what's used for the evidence accumulation. Um, yeah, so I guess you're right. It's not exactly the active inference formulation where what you would do here is you would well, I think yeah, they're very closely related. But if you were to formulate it, in standard active inference terms, you would have the expected value be converted into a preference prior by taking the Boltzmann distribution over the values, and then you would compute your classic pragmatic value using the essentially log p of that, which I think is very similar to this, and the lambda parameter would get absorbed into that preference prior distribution
Yeah.
rather than being multiplied by the EIG. But I think these are, I think, essentially very similar in spirit.
And you would, to get the expected, like you would also need to run your predictive posterior, right? You say, if I do this, what's the observations I'll get? And use that to calculate both the epistemic. Do you do that anyways explicitly? Like, does this agent have, it has a generative model of the environment where it knows if I look here, these are the observations I'll get.
Yes, so that's captured in these between and within trial beliefs.
Right. Yeah, exactly.
Yeah, so this tells you, if I look here, what's the likelihood of seeing a particular observation given given different possible hidden states, and then also for between trials.
So I
Yeah,
suppose the question is, why not do that?
sorry.
Why didn't you do that? I mean, not in a just in an open
Uh,
question, right? Given that you're here today as well, so there might be many good reasons that you didn't, from implementational to rhetoric in other fields and so on. But so for this specific choice, but also in general, uh, open question to do you know, would it be nice to try and make it, let's say, fully classic active inference? And I think it would be exciting in general to have a general way of mapping an active inference model to this kind of time-sensitive course with
yeah,
reaction times and so on as well. If you think it's too hard, or maybe other people wouldn't want to read your papers if you did it, or
no,
uh,
no, no. I mean,
open question.
yeah, I think that there's definitely lots of things that could be brought in. So also here we're using a Bayesian update, but you can as I mentioned, relax that to the variational setting. Um, yeah, I guess it could be formulated within the active inference framework. I think initially, sort of where I was coming from with this is, I was reading a bunch of papers in the evidence accumulation literature and cognitive neuroscience, and they typically formulate things in terms of values and these
Yeah,
sorts of things. And so I think just the way that it came together in my head was in terms of those things.
yeah.
Yeah, that's definitely, I think, very natural to extend it to make it fully active inference.
I mean, yeah. Maybe I was thinking one advantage of that would be that you could take some other given task, maybe. Uh, Maybe not specifically this kind of task, but other active inference tasks with planning and with whatever, and try to get at reaction times or time courses of updates or gaze tracking or something like this with those, which is, of course, interesting to me. Then I could take the David map and use that in my own models.
Mhm. Yeah, that's something worth exploring.
Hmm. All right, I think I'm through the most important ones. I'll just give people another chance to raise their hand or write in the chat if they have anything. And I'll check my own notes. Okay, I have a tiny one more,
Mhm.
two tiny ones, but they're almost yes or no questions. So you used the where people fixate, but not how long they fixate at a given place for your
Yeah,
model. Is that the standard in the field? Do you think that's a, because it kind of makes the continuous time course into discrete actions again in a way, which is
yeah,
makes it easier. Yeah.
yeah. I think you're exactly right. So there's some variability. I think people typically aren't able to predict how long a given fixation will be. And so it's typically, or at least in the papers that I've seen, is broken down into these kinds of discrete fixation events. Um, I think intuitively you would imagine that if something is fixated longer, that therefore there would be more time for evidence to accumulate for that particular fixation. I don't think for this data set that information was recorded.
Yeah.
So all I had was just the sequence of fixations. But I agree, like if you were to add that information, then it should improve the ability to fit. Um, yeah, but maybe there are papers that do this.
It seems in that case, the model would not have to only choose where to fixate, but also choose how long to fixate based on
Yeah,
some kind of expected reward and stuff.
yeah.
Which-
So I think there was one paper that was sort of formulating the attention as a kind of essentially a Markov chain. And so
Mhm.
you could the Markov chain could loop back to itself, which means that you're kind of like staying on a particular fixation. Yeah, and actually in this data set with the consumer choice on the phones, I looked at the initial fixation distributions and how those how sort of like the transitions worked. And
Mhm.
there was a very strong bias towards refixating the same option. Um, but there was also biases towards shifting to the same feature of the other alternative, um, and also staying on the same alternative. But when you were going to shift from shift to a different feature of a different alternative, that typically occurs less frequently.
Interesting.
Mhm.
And so people want to keep looking at something to keep
Yeah,
it.
and this kind of like comparison process happens between different alternatives on the same feature. And that's quite a strong effect.
So then a last conceptual question, because it seems to me that the model, essentially you look at something, but you don't completely see, correct me if I'm wrong, you don't completely know what that feature is. Like it takes a while to realize that when it says 500 watt, whatever, then that's the actual value of that feature, right? And
Yeah, yeah,
it's only worthwhile looking at something until I know what it is. Or is there an implicit value of just looking at 500 milliamps, 5,000 milliamps itself?
yeah. So this is a phenomenon known as value-driven attentional capture. And basically, the idea is that things that are valued intrinsically draw your attention, even though you've already, let's say, resolved your uncertainty about the underlying state. So yeah, like people will just look at a feature that they value, even if it's not going to be informative. And interestingly, they did these experiments where people were essentially rewarded for like picking a particular alternative, and then in a new trial where that alternative was no longer rewarding, their attention would still be drawn to that.
Yeah.
So it sort of like captures their attention, and then also, obviously that causally influences the evidence accumulation process.
So we're kind of implying that people like looking at things that are good. You know,
Yeah.
I would
Mhm.
look at a number saying the screen is bigger more just
I
because,
would Yeah, I would say maybe people like looking at things that would also resolve uncertainty about which option is best.
yeah.
Um, and there are also lots of nuances here because people are loss averse, and so they tend to also like fixate on things that seem like really bad uh, or like really really strongly negative outcomes. So yeah, there are lots of different effects to disentangle here, but yeah, broadly they kind of pay attention to the things that matter to them.
Because from just from introspection, when I was
Yeah,
doing the task,
yeah,
looking at something, it doesn't take me very long to know what it says.
right, exactly.
I don't need to keep re-looking at this 5,000 to know that it says 5,000. That I know this maybe on the first fixation or something, or the second.
Mm.
Who knows? Maybe my introspection is wrong. But it seemed to me that the hard part was to keep them all in memory.
Mm.
So the one I'm looking at, I
Yeah.
could remember, but I couldn't
Mhm.
remember all the other one at the same time.
Yes. Yeah. This is something that I think would be a nice extension to the model. It's unclear how I would do this in a principled way, but yeah, I
Right.
agree that working memory is an important factor. And so, once I fixate something, I update my belief and now I'm certain about it. And then in the way I implemented it in our experiments, that belief just remains like that. But yeah, you can naturally think that it sort of kind of gradually decays if I haven't fixated on it for a while.
And you could imagine that that would lead me to look at valuable things more because those are more dangerous to forget.
Yeah.
Yeah.
Yeah. And yeah, we do see this in the empirical data, people like refixate things multiple times throughout the course of an
Yeah.
episode. Another interesting thing that is like very strongly observed in the literature is that people tend to fixate last on the alternative that they're going to choose. So like
Yeah.
if you look at the final fixation, it's usually the thing that more or less that they're going to choose.
Yeah. Which this
And
makes
Yeah, that's consistent with this kind of evidence accumulation idea, where because you fixated on that, it's going to accumulate evidence faster, and then it's going to cross the threshold.
Yeah, that makes sense. All right. Thank you, David. I have no more. Last
Yeah.
chance for others in the group to ask questions or provide comments or feedback for David. Otherwise, I do think it's Carl's turn.
Is it my turn now?
I think so.
Very good. Thank you very much. Yeah, that was an excellent presentation and a very thorough question and answer from Peter. So there's not much left I have to say, really, is there? So let me, yeah, as usual, I've been going through whilst listening to the presentation and the conversation afterwards, picking out potentially relevant papers. And I have to ask myself, relevant to what? So I'm just standing back and thinking, how do you want to pursue this work? How do you want to promote this work? How do you want to take it forward? And I think, implicit in some of Peter's questions was there is, I think, an opportunity here for joining the dots between two different communities. And we're talking about sort of classical cognitive science, evidence accumulation, race models, drift diffusion, all that good stuff, and the active inference community. And I have to say, with all arrogance and the fond hope this is not being recorded, I think active inference is going to take over. Basically, I don't think you need to worry too much in 5 or 10 years' time about sort of evidence accumulation and drift diffusion models anymore, because they are just colloquial formulations of Bayesian filtering, basically, which is subsumed under active inference. However, at this stage, I think there would be a great opportunity to show the equivalence between the two. And you're clearly very well versed in that literature being pursued out with active inference. And therefore, but also you are also engaged in the active inference community, which means that you're in a sort of privileged position of being able to sort of do it both ways and show the formal equivalences. So that would be one strategic way of sort of leveraging the work you put in, saying, look, I've taken all these sort of established devices like evidence accumulation and the like, and I've reproduced the kind of behavior that one sees empirically, but also the kind of behavior that one can simulate under a first principles account, which is active inference. And I use the word first principles account because in active inference, you're not allowed to pick this particular scheme or put in a noise term on your that's artful and very creative, and it's a great game to play, and it's the kind of game that people in sort of computational neuroscience and cognitive neuroscience have played for for decades. But in active inference, you're not allowed to do that. You have to show all these things are emergent properties of a variational principle of least action. And that's the challenge. It's showing that these things emerge under particular constraints on the imposed by, say, the task, or imposed by the the implicit generative model that the subject is actually using. So that, I think, provides a principal motivation for joining those dots. If you can show that, for example, using an evidence accumulation scheme emerges from or can be derived from a pure active inference implementation, then you're also endowing decades. I was tempted to say centuries, but I think it's more decades than centuries. Decades of commitments to things like evidence accumulation, and lots of other little things that you introduced. you're endowing them with a construct validity and moreover a face validity in relation to sort of first principle accounts. So that would be one strategic way of going forward. It's not actually to sort of just do it all again using vanilla active inference. It's more showing the links between the two. And that would appeal to two communities. It would appeal to the communities that are still in the drift diffusion world, and and that community, it may be sizable. I don't know. I don't bother reading that literature, but it may be a sizable community simply because they've grown up thinking this is how you model this kind of thing, and therefore they don't look beyond that. Their attention is limited to their favorite drift diffusion model, for example. Um, but if you can sort of, they would, I think, appreciate saying, well, yes, that was quite exactly the right thing to do. That this is if you sort of rewrite a first principle account, then this is exactly what emerges from it. So well done. But also it would be engaging for the active inference community. I'd be interested to see if they've just come to active inference, then in fact, people have been using the right kind of tech and the right kind of sort of update equations in one corner of the problem space. I think to do that, though, you're going to have to know the literature in active inference that pertains to this to do that properly. So I did try to pick out a few papers that you may well have read, but may have forgotten. But I think somebody like me would expect to have covered if you wanted to sort of relate those things. And there are lots of interesting issues you touched on, like sort of this notion of putting the cost in explicitly into a value function. That would be one example of a commonsensical heuristic, which keeps on coming up every 5 years or so, which is an emergent property of of active inference and a sort of variational approach, both at the level of the risk, the KL divergence between anticipated and preferred outcomes, which is an expected complexity cost, which then via Landauer's principle can be written down as a thermodynamic cost. So you get that for free. And that's an emergent property of active inference. You don't have to sort of put it in as an extra ingredient in your objective function. It's there if you take the first principle account. But it also emerges, I think, in terms of things like cognitive effort, beyond just a computer scientist trying to work out the most efficient, the path of least action for this particular computation or inference. Then there is a field in cognitive neuroscience about the effort it takes. So can you understand this in terms of effort, which would be, I think, another useful, well, it's a useful point that came out in your discussion, but also something that you could celebrate should you want to write a sort of a synthetic paper that sort of again sort of joins the dots between sort of various fields in cognitive science in this instance, as opposed to computational neuroscience. So that's why I picked out a few papers, and also to remind myself to make a few points. I should also say, though, that you're in the very rich presentation, rich in the sense you covered lots of issues. You also spoke to a completely different area of great pragmatic value, which is basically fitting empirical choice behavior and reaction times and the like under a formal model of choice behavior. So that's I think and using that sort of LMNE. Have I got the acronym right? Yeah. What is it?
MNLE.
Right. Which I presume is a form of amortization, just parameterizing a likelihood mapping within your neural network. So that was very interesting, and I'm just sort of counseling that don't bundle these two things together strategically, because people may not be terribly interested about the sort of mathematical links between evidence accumulation and a Bayesian filter, but they will practically be very interested in how can I quickly score this patient in terms of some hyperparameters or some prior beliefs or some temperature or precision parameters. If they're working in the field in computational psychiatry, for example, that would be very useful. And certainly that's something that Peter is very interested in terms of his Julia package. It's something that people like Connor Hines is extremely interested in terms of PyMDP, which is why you were being asked, what software package did you use? Because both the Julia implementation and the PyMDP implementation, and particularly the use of JAX, are aimed towards doing exactly what you were aiming towards with your sort of fast and efficient fitting of empirical, subjective responses. So I thought that was very interesting. It reminded me of sort of likelihood-free approaches, which if you can amortize, that would certainly be another well, you can if you can do it fast and efficiently, that a lot of people will be interested in that. And I think also, Peter, the hierarchical Gaussian filters are trying to move in that direction, isn't it? Well, perhaps
in the direction of likelihood-free.
well, no, I mean I'm talking about likelihood-free as one sort of fitting device. But I just get the impression that Chris is trying to sort of generalize the HGF that accommodates hidden states, and thereby make it more generic in terms of fitting to reaction times or choice behavior and the like. Yeah, I'm just making the point, David, that that particular agenda of making of being able to put your favorite model into in place that can explain empirical choice behavior and reaction times and psychophysics is a big thing. And just to separate the agendas of writing your theoretical paper and writing irrespective of whether you're using active inference or evidence accumulation or your particular admixture. There are generic. There's another offering on the table here, which is basically a fast and frugal way of phenotyping. So this usually comes under the rubric of computational phenotyping this person in terms of their prior beliefs. And that allows me, before I forget, and I haven't got a paper to remind myself to say this, but before I forget, you should always mention the complete class theorem when discussing this issue. Do you know what the complete class theorem is?
Yep.
Yep. So explain to the reader and potentially user that for any pair of loss functions or prior preferences and behaviors, there is always a first principle Bayes optimal explanation for the observed behavior under some prior beliefs of that subject. So that has, I often find myself sort of saying this out loud to audiences. That has two implications. On the one hand, that basically means you can always tell a just so Bayesian story about anything. So that's sort of acknowledge people like to hear that because a lot of people outside Bayesian brain hypothesis and predictive processing active inference get very upset about the just so stories. And if you can say yes, there's always a just so story, and you can prove it with the complete class theorem. However, what it means practically, it means that there always exists a description of this subject in terms of their behavior, or given their behavior, either psychophysically or in choice behavior, and the priors that underwrite their generative model. There has to be, it always exists, which means that in principle you can always estimate it. And then you can sort of say, well, what do I mean by the priors of this person's generative model or observation model? Anything that parameterizes their belief updating is going to be part of their generative model. And usually the most important things are the precisions. For you, they are the temperatures or the inverse temperatures. They are the lambdas and the and the all the different sort of balancing coefficients or rate parameters. So in that spirit, I think there could be a lot of mileage in just sort of saying that focusing on computational phenotyping to identify the most plausible precisions, inverse temperatures, softmax parameters, is not only a really intuitive and useful way to proceed, it is, if you like, mathematically a viable way forward because of the complete class theorem. And furthermore, what you can say is that, look, the parameters that I needed to optimize, I only need to optimize two, theta and lambda, I think it was. They're both precisions. When you put them, put them inside the probability distributions inside the log, they always become precisions. So that I think would please a lot of people in the active inference community, particularly in the computational psychiatry, because that's how they think about when the brain goes wrong. It's not the sort of structure of the generative model. Usually, it's not the prize on the content. It's just getting the precisions wrong and getting the wrong balance between this and that, which usually is the best explanation for most psychiatric conditions. So yeah, I just wanted to make that point. I'm not going to come back to that, but just to sort of reiterate, computational phenotyping and devices to do that are an important field, which I think you should sort of focus on in terms of strategically finding a home for this. And now you're looking at sort of things like translational psychiatry or computational psychiatry, getting invited to the computational psychiatry workshops just to show this. Peter will be in a good position because he's now back in Zurich, where they have the annual computational psychiatry workshop, or one of them, the Zurich one. So let me just briefly go through the papers that came to mind while you were talking. And you can now this has been recorded, so you can sort of go to sleep if you want to. But if I mention a paper you hadn't seen before that you want to come across, you want to read, you hadn't come across before, and you want to read, then you'll have access to it. I've chosen them really to. At the moment, you seem to have read the literature that people like Mike Shadlin and friends, would be comfortable writing. There's another domain of application which is much more clinically orientated, which would not subscribe to that style of thinking, but much more, how do you actually explain bedside tests of this kind of attentional deployment or salience, and how it can go wrong. So a couple of papers I put up there are from the theoretical neurology literature, which is addressing exactly the same the same issue, which it would be, I think, useful just to point to or to nod to, because you could sort of reinterpret the structure of the generative model in the game that you've showcased in the presentation, I think quite easily to the kind of bedside tests that people actually use in practice when trying to assess whether this subject has, neglect syndromes, for example. So that would be another potential audience that you could speak to, which is not quite the computational phenotyping psychiatry, but more trying to understand mechanics that underwrite these clinical neurological tests of how people use attention or salience. Before I do that, can I just ask you? I didn't quite understand the evidence accumulation part, and I'm guessing that. So correct me if I'm wrong. When you talk about attention and the allocation of attention, you're basically talking about looking at this part of the visual scene, which holds some visual cues that provide sensory information to resolve uncertainty about something. And you talked about features. which I'm reading as sort of as latent states that best explain the visual information. And the evidence accumulation, then, I am imagining takes place while I'm looking at a particular, say, the screen size location in the iPhone thing, and therefore what you're actually modeling is a very detailed evidence accumulation scheme where one could model this as basically I'm going to look over there and I'm going to look over there, but while I'm looking over there, I'm going to accumulate evidence for at a particular rate over time. And then at some point, I'm going to look over there and then do the same thing and accumulate and remember what I've accumulated looking at the different places. I see. And then that's all sort of within trial. And then the between trial is what happened when I've actually made my selection. I see.
Yes.
So that's quite a sort of detailed, which is good because that kind of thing, as you say, becomes relevant when you're actually trying to fit reaction times and dwell times. And certainly in sort of the dot cancellation test, which is the kind of test that you'd use at the bedside, you'd be scoring how quickly do people do it, which makes that particular part of the model important. I see. Okay, good. So I've answered that. So we're not talking about covert attention, where we're not be well, I suppose we could, but the very fact you mentioned that some of the data sets had eye tracking. Sorry, what I'm thinking here is that there is a field or there is a distinction between equating visual salience with where you are looking in terms of explicit saccadic eye movements, which are the way that you'd empirically access this. Speaking to the classic work of Yarbus and the whole visual search literature, and that due to things like the premotor theory of attention, where you're actually fixating, but you can start to attend to different parts of the visual field on the inside. So it's like eye movements on the inside just by sort of assigning more or less precision to different parts of the visual field. That's an interesting sort of extension of this work. But the fact you're nodding, then I'm now reading that the moment you're equating the deployment of attention with just basically where am I looking now, and so we're in the visual domain, which is good because of course then you can measure where you're pointing. Okay, right, and therefore I see. So
yeah, and maybe just one thing to add. So whatever you're fixating on is accumulating evidence at a faster rate, but the unfixated alternatives are also still accumulating evidence, just at a slower rate.
okay, that's interesting.
Yeah.
Okay, yeah. So on that view, so you've already had this conversation, but a Bayesian filter, a Kalman filter is evidence accumulation, and predictive coding is evidence accumulation, and predictive coding under a continuous state space model is active inference. So these things are all mathematically identical. And that's been celebrated in various fields, and that's the kind of thing that you want to be able to say. The functional form of an evidence accumulator just is a Bayesian filter, and Bayesian filter just is one aspect of active inference. The only difference with active inference is you've actually got action in the mix, but otherwise it's just basically Bayesian filtering under continuous state space models. So that would be one easy thing to do, and it also would allow you to write a paragraph referring to all the classic literature on evidence accumulation, just saying that this is formally identical to predictive coding and in sound file compression and neuroscience or Kalman filtering in engineering or model predictive, no, of course that's active inference, but model predictive control in control theory. So if you just join the dots and say these are all the same thing, I think that would be one useful example of how to put it together. I didn't fully understand, though, what the evidence seemed to include the epistemic affordance as well. So that was a little bit confusing for me, but I'll let you try and resolve that confusion with your readers as opposed to trying to.
Yeah. Well, so I guess the basic idea there is that the expected info gain term in the drift is essentially a kind of curiosity bonus. So if I see a flavor of ice cream that I've never tasted before, then that curiosity for tasting that ice cream is sort of like points for choosing it. And so that's why I sort of added it to the drift.
Yes, I think I understand. So I'm having to think about, how that would emerge from a vanilla active inference implementation, and I'm guessing it would emerge in the sense that your policies would be to actually shift your attention. And as you say, you can shift your attention by not moving your attention and dwell on the same, if it's noisy information that's coming through. And therefore, I'm reading your your attention thing, as basically as effectively the expected free energy of moving or looking over there. So in active inference, in vanilla active inference, all of this would be slightly simpler. You just write down this attentional policy means I'm going to look over there, and continue looking over there. And I just want to take the path integral of the expected free energy, and that path integral could be over time, and then you can get your sort of get your evidence accumulation device in, and then I am now going to commit to then I act and then actually prosecute my chosen attentional allocation. I look over there, and then the game starts again. And yeah. Anyway, good. Right. So very quickly, let's go to share if I can, and we need to.
Yeah, so maybe can I just ask a quick question on this last point that you mentioned? So one of the kind of, I guess, limitations of this model is that it's sort of using a one-time step ahead formulation of the EIG and the expected value, which, like, I guess in the more modern sophisticated inference versions, you're actually doing these rollouts over time. But I guess the question is, if you are also computing these sophisticated expected free energies while you are doing this fixational sampling, then there can kind of be two sort of timescales at which this is happening. I'm not sure if that makes sense, and how this might be resolved.
Yeah, well, no, that's a really good point. So you're absolutely right. So if you're doing active inference and you're evaluating the probability of making this attentional move, looking over there or attending on the inside to this, that evaluation and that tree search, where you're accumulating down every branch of the tree, the path integral of your sort of objective function, which which in active inference would be the expected free energy, because it's expected in the future. That all has to happen before the next action or the next move, and that means that you've got some very, very fast updates that are going on in virtual micro time, as it were. So you plan your future in your head very, very quickly before actually making your move, and that is manifest in empirically in many different ways. If you're an electrophysiologist, you would be interpreting that in terms of something called pre-play. So if you record neurons and neural populations in small animal models, in deciding which way to go at the junction of a T-base, for example, then you can sort of record very fast simulation pre-play events. I go that way, and I go that way, using sort of place cell responses. So these are really fast. They can happen within 50 to 100 milliseconds. And then the animal commits to either going this way or that way and actually does it, and then has a rest, and then works out the next place it's going to run to. So there's this separation of timescales between the planning and the execution, which introduces a certain temporal scheduling, a saltatory aspect to action. And another way that this is manifest is that we, wherever you look, the way that we actually deploy attention physically happens in a saltatory way, roughly every 250 milliseconds. So in terms of saccadic eye movements, we move about 4 times per second. If you're a little mouse, you would be whisking at the same frequency, palpating the world with your whiskers as opposed to your eyes, about 4 times a second. And that in the electrophysiological world and possibly cognitive neuroscience world would be associated with a theta frequency. And then you go to another literature, which is all about theta gamma coupling in terms of measuring the dynamics that underwrite the neural message passing or the belief updating or the evidence accumulation, where you get these fast gamma fluctuations in electrical activity that are entrained by a theta cycle. So the idea is when you simulate this kind of path integral of the expected free energy, which would be sophisticated inference in its full blown variation, then you associate the fast activity, like sort of very fast pre-play, as measured by, say, gamma activity, with the planning, and then after you've done your planning, you do your move, and then you start planning again. So you're absolutely right. There's a separation of timescales here. You had that in your presentation. You do the sort of the within between trial, and then within and between actual eye movements. Within eye movement, you've got your evidence accumulation. So you've got that sort of separation of timescales in your simulation. Usually in simulations of this sort, where you actually do multi-step policies into the future, which would require a path integral into the future, that's done very, very quickly. And also, interestingly, if you know, again, this is probably off topic for you as a computer science, but it is interesting. You may be asking, well, how on earth does the brain evaluate the paths into the future for all possible places I could look next? Because there's an infinite number of points that I could saccade to in the next 250 milliseconds, and even if I look just 50 milliseconds ahead, or look to the point in time where I've actually made my saccade in the future, I've still got sort of potentially sort of an enormous number of different policies. So the way that the brain handles that is to do your evidence accumulation in parallel in a map. So you've got something called the superior colliculus, which is a subcortical organ in the brain that has a layer. People believe that this is where there is one of these salience maps. And what that basically means is that your S signal, I may be wrong, but let's pretend that the S signal is a salience and it's the path integral or the softmax of your expected free energy. You evaluate that for every point that you could look. And then what tends to happen is that as you accumulate the value of looking over there, then this part of your salience map starts to accrue much more activity, and the rest is suppressed. And at a certain point, which would correspond to your threshold, you then trigger the eye movement. So basically, you are paralyzing the planning into the future conditioned under every policy, where each policy is where I'm going to look next. And you can do, hundreds of thousands of policies, all jointly evaluated in a biologically plausible way through this saliency map idea. Is that what you were driving at?
Yeah, that's really interesting, actually. I hadn't thought about it that way, but yes, because in this model, the evidence accumulation is happening for which alternative I'm picking. I think what you're describing is that there's also a kind of a nested evidence accumulation model, even for the sort of the action of where to look next.
Yes. Yes, yes, and I should have made that clear now that you've clarified where your evidence accumulation is operating. Yes, you're actually simulating a situation where I've actually saccaded, and now I'm going to spend 200 milliseconds accumulating evidence, and potentially quite noisy evidence. So I'm going to accumulate having made my saccade, and then after that 200 milliseconds, I'm going to take 50 milliseconds to move my eyes again. But before I can move my eyes again, I'm also simulating the future, doing the planning, which is completely different from the evidence accumulation. So when I talk about the path integral down the decision tree of every place that I could possibly look next, that's a completely different kind of evidence accumulation that you've simulated. You've simulated the actual staying in position and accumulating the evidence primarily from the point that I'm fixated on. To update my beliefs, so then I can then do my planning for the next move, which sounds very much like the way that the brain actually does work. Yeah, so they are distinct things. Yeah, the path integral of the expected free energy for planning is separate from the evidence accumulation, the Bayesian filtering of visual stimulation once you've made your move and you've committed to looking over there. And that's an important point to emphasize, because, of course, you've now got the opportunity to explain dwell times and the frequency of eye movements, because you're actually putting that in as part of the part of the model. I've got this up just for fun, because it's a very old one, but it does. This was a very early simulation of eye movements that were driven by the salience as scored by the expected information gain. But in using a continuous state space model, so using filtering. In this simulation, the subject knows that she can be looking at an upright face or a sideways face or an upside down face, but can only look at a very small, she can only attend to a very small portion of the field. So the attentional allocation here is deciding where to move next, and clearly has to work out where is the most informative way, what has the greatest EIG in your nomenclature. And it was simulated in a way that speaks to these salience maps, these superior layers, superficial layers of the deep layers of the superior colliculus. So these are the salience maps. So these basically are maps of the expected information gain, or that you would get if you looked over here or looked over here, looked over there, looked over here, and then you make your move every 250 or 200 milliseconds in this instance here, and this is what you see. You only ingest the data while you're actually fixating on this particular point. Then you move on to the next point in this saltatory way. And resolve your uncertainty in the most efficient way about whether it's this, or this, because you picked the parts of the visual image to sample that have the greatest expected information gain. So this is using sort of the rhetoric from the visual search literature that a neurobiologist or a visual physiologist would understand, but has, I think, a nice connection to the kind of paradigms that you were talking about, particularly because you've actually got this continuous evidence accumulation under uncertainty written into it. I just like this. It took me a long time to prepare this graphic when I was younger, so I'm indulging myself showing you, which I shouldn't really be indulging myself. So yeah. I'm afraid I can't find the original this paper, but this I put this up just because I think it would be nice for you to include in the discussion of your work the kinds of bedside tests people use as a clinician in outpatients that could, in principle, be modeled using the kind of setup that you have. Effectively, this is a sort of dot cancellation test. Oh no, I remember, you won't actually load. I'm sorry, you're going to have to go to the find the original version of this written by Thomas Parr. So this is a classic neurological test where you ask people to cross out as many dots as they can in a limited amount of time. And the reason it's used is that with some people who have certain lesions, usually parietal lesions, have an attentional neglect, as if they cannot accumulate. Sorry, they can't attend to, and therefore saccade to complete halves of the visual scene. It's called hemi-neglect. It's as if half of their visual world just did not exist. And the way that you demonstrate that and test for it in the clinic is to give them a piece of paper with lots of dots on the right and the left, and then ask them to cross out all the dots. And what people with these hemi-neglect syndromes do, they're great at doing all the dots on the right side of the piece of paper, but just don't see or ever attend to the left ones. And it strikes me that that would be a nice way to lesion your model and then show that it reproduces the hemi-neglect that people actually see using these kinds of tests. Unfortunately, I can't show you the graphics, but I'm pretty sure that Thomas simulated the dot cancelling paradigm and then described this in this particular chapter on novelty and neglect, and then went on from that to actually use electrophysiology, I think actually, magnetophysiology, and the biophysical modeling. So this is not computational phenotyping, but it's actually given the hypothesis about the attentional allocation. So the likelihood of attending here as opposed to attending there. Understanding that that is probably encoded in terms of postsynaptic gain and synaptic efficacy, we're able to then estimate that using dynamic causal modeling in subjects. And that, so this would be an interesting read from your perspective of how a neurologist would understand the problem, and and how an electrophysiologist would start to use this kind of modeling to generate hypotheses for the functional anatomy of salience, and start to sort of test hypotheses empirically using electrophysiology. So I thought that was just to sort of expose you to another field, another way of thinking and using these models of salience and attention in a practical way in the context here of neurology as opposed to psychiatry. Yeah, so we've done those two. That's very good. Yeah, I'm just putting this up because it did cross my mind that in the full-blown, as you discussed, the full-blown account of this, you'd probably want to do not just one step ahead, but 2 or 3 step ahead, and not just on the expected utility, but the expected information gain into the future. Having said, and the mechanics of that would be, as you say, sophisticated inference. However, I really wouldn't worry about this. Nearly every sort of application domain I have encountered, you can do 99% of the heavy lifting just looking one step into the future. Um, and certainly when it comes to the simulating very plausible eye movements of the kind that we were just talking about, you would just need to worry about what would happen if I did that. And that's just one step into the future. That's usually 99% of what you need to. So I wouldn't worry about this. And if you did want to worry about this in the future, in fact, you would probably not use sophisticated inference and all the computational load that entails. You'd move to something called inductive inference. Once you've developed very precise beliefs, that's much more efficient way of getting deep into the future, should you want to. But for completeness, I put that up because it was mentioned. This paper, I'm going in reverse order. I put this paper up because I was interested about your conversation with Peter about sort of the computational cost, but also there is a cognitive effort cost. So cognitive scientists, as opposed to cognitive neuroscientists who know about computer science, have another view of the cost of making a decision of usually an epistemic sort that is going to entail a lot of effort in terms of moving my beliefs away from their prize, inducing a computational cost in terms of the KL divergence or the complexity cost of my belief updating. And when applied to action or distributions over attention or policies, where I'm going to look next, you can make a good argument for cognitive effort being scored as the degree of movement that is entailed by committing to one policy or another policy, where the movement is that the KL divergence, or summarized by the KL divergence. So I thought that would be, and again, you should be able to pick up out of your simulation these quantities because you've got all the KL divergences there, and there will be one that corresponds to cognitive effort. And you can read about the what particular KL divergence seems to explain cognitive effort in this paper here, which I repeat is distinct from the computational cost, which is just basically the cost of Bayesian belief updating, which is implicit in the risk term. If you rearrange the expected information gain and the expected utility, you can rearrange it into risk and ambiguity, where the risk is the KL divergence between your anticipated posterior conditioned upon an action and the prior preference, plus a conditional entropy, which is an ambiguity term. And that risk term is just the expected complexity. So it's the expected cost of belief updating if I did that, which is closely related to the sort of the Kolmogorov complexity of of a particular computation. And I repeat, you can chase right back to the metabolic and thermodynamic costs through things like the Zielinski equality. But this is not that. This is much more for cognitive scientists. I mentioned this before. It just might be worth. Well, Peter's a second author, so he should know all about this. So I've just kept my eye on developments in the hierarchical Gaussian filter. You've talked about volatility models. You talked about the motivation for putting the leak term on the evidence accumulation. And of course, that's kind of Bayes optimal forgetting. It's absolutely essential in the context of volatility models. And the sort of the go-to model for this kind of volatility in the neurosciences would be the hierarchical Gaussian filter. And I am aware that it has recently been generalized. So previously it was just restricted to working out precisions or inverse temperatures, but it's been generalized recently. Peter, did you want to comment upon that? Or?
I mean, I think we also discussed it a little bit, David, but the generalization just means that you can also filter the means, so it gets a bit closer to generalized filtering schemes and so on, which that's a whole different discussion. But indeed, as you say, Carl, in the CompSci cognitive modeling world of volatility learning, that's a standard model that indeed has this forgetting rate being higher when the environment is learned to be more volatile.
And this would be an example for you, David, where at some point in the discussion or joining the dots part, the thesaurus part of your work, you could say, we've we've borrowed this leak term from XYZ 1962, but actually it is a crucial and emergent property of Bayes optimal inference, as evinced by the hierarchical Gaussian filter that is designed to accommodate volatility or fluctuations in the precision of the dynamics of any environmental world. So it's just another example of saying, it's these sensible bits that you put in are motivated from a first principle account, and then just pointing people to where that first principle account can be accessed or can be read. So I don't think anybody's suggesting you should use a hierarchical Gaussian filter. It's just know it's there so that you can say this is what the hierarchical Gaussian filter specializes in. And that sort of lends a construct validity to all the little bits and pieces that you picked up from the sort of the era before things like the hierarchical Gaussian filter. Yeah, I just wanted to make just come back to this careful use of the word attention and salience, which is, it is can be a vexed issue, and it's always worthwhile, I think, sort of being very clear about how you're using attention and salience and related terms. They're very clearly defined in the active inference literature, and to be again quite honest and polemic, I don't really care what other people call call things. The expected information gain is the salience. It's just that part of the expected free energy you get if you don't have any preferences. Is that attention? I think it is attention, but you'd have to carefully qualify that, because a lot of people in active inference also associate attention with precision weighting. So that introduces, I think, an interesting distinction between two kinds of attention, which Peter referred to as overt and covert. I think a better way of carving attention into two different kinds would be what's called exogenous and endogenous attention. And from your point of view, the exogenous attention is that where local computations are sufficient to adjust the estimates of the inverse temperature or the precision, and without any planning. Whereas the exogenous attention rests upon a particular plan and the computation of the salience in terms of the Bayesian surprise or the expected information gain. So in the visual search literature, Bayesian surprise, well, the expected Bayesian surprise is literally the expected information gain. So when you're talking to visual search cognitive neuroscientists, when they will read the expected information gain, the EIG, as Bayesian surprise, as salience. That is salience for them, and that has got nothing to do with adjusting the precision of, say, visual prediction errors in the context of trying to simulate Weber's law, for example. But the interesting thing happens, there's an interesting situation where your plan, your policy can actually be the precision weighting. So now you've got endogenous attention, controlling exogenous attention, and then you can start simulating things like the Posner paradigm. But from the point of view of active inference, I think it's important to tell people how you're using the attention word, because most people like Jacob Howie, for example, and possibly even Andy Clark, will immediately assume you're talking about precision weighting of prediction errors under a Kalman filter-like sort of view. Whereas what you've been talking about is very much an explicit information-seeking aspect of the way that we actually actively sample the world in the sense of visual palpation and active vision. And that basically, that's the heart of active inference for discrete state space models based upon the expected free energy. The other sort of, if you like, or the accompanying dialectic is between continuous and discrete state space models in order to evaluate the expected free energy or the salience in the absence of an expected utility of a discrete number of places I'm going to look next, you have to have a discrete number. If you're in a continuous formalism, there are an infinite number of paths into the future, and you just pursue the path of least action. That would be sort of the exogenous attentional precision weighting kind of attention, whereas you're talking about the sort of more discrete MDP-like selecting amongst a number of points that I could look at. I could look at one of these 3 points on the iPhone. There's a discrete set of choices I have to make. If you wanted to read about the computational neuroscience implementation of precision weighting of this exogenous sort that has no planning in it, this is probably the most interesting paper, which basically shows how this looks like feature ground separation when just getting the inverse temperature or the precisions right when processing visual information in a continuous setting. Nothing to do with what you've been talking about. What you've been talking about is, well, actually, no, to a certain extent, it is what you've been talking about. So, in virtue of the fact that you are accumulating evidence more quickly from the attended or foveated part of the visual scene, that would be exactly a precision weighting. That would exactly be some planned increase in the precision afforded to this part of the visual scene, so that you accumulate evidence more quickly. So from a race model or a drift diffusion model, it's the slope of the evidence accumulation. So the slope of the evidence accumulation is the precision. It's under the hierarchical Gaussian filter or Bayes optimal evidence accumulation, it would be the sort of ratio of the prior to the ratio of the sensory precision to the prior precision. So the people use sort of these drift diffusion models to sort of disambiguate between the sort of the precision and the thresholds of the sort of when they plateau. And the offset is the prior. So in these evidence accumulation models, the slope is the precision, the offset is your prior bias, and then your threshold is when you cross your threshold. So if you're interested, again, you probably don't need to, but if you were interested in just seeing how you'd implement a pure Bayesian filtering with automatic adjustment of the Kalman gain with no planning, and how far you can get in terms of explaining this kind of exogenous attention, this would be probably the best paper that takes you through the neurobiology. On the other hand, if you want a sort of careful distinction between salience and attention and working memory, I'd recommend this by Thomas Parr, who sort of says it's not quite that simple if you're just a precision weighting person. That you were effectively simulating in the evidence accumulation part. There's also where you're looking to accumulate the evidence, and that's of course the planned part, and that would be salience in my world, but obviously a really important aspect of attentional deployment. You have to evaluate the salience of a particular cue or its affordance before you can attend to it. If I remember, I think this is a nice discussion of that seen through the lens of an active inference person, but also a neurologist who's using this to understand neurological conditions. You mentioned that. I just put this up because you mentioned Philip Shortenbeck's original work, where you have to sort of keep track of time and the like. If there was anything useful. Oh, right. Yeah, I think this is probably going to be the most relevant for you in terms. Have you looked at this work by Burke Mirza?
Yeah.
Oh, good. Okay. So this was a sort of more up-to-date, discrete formulation. So that Pulvina paper done with Reuter was based on a continuous state space model, whereas this is the equivalent in of treatment of salience attention in a discrete state space model. I can't remember the details, but I do remember thinking that you would be very interested in that, and clearly you are because you have read it. Yeah, so computational phenotyping, interestingly done by the same person that invented that sort of waiting game, very early demonstration of exploration and exploitation in a discrete setting. What's this one? Oh, right. Yeah. Do you know Pedro Ortega and Daniel Brown?
Yeah, Pedro is a good friend of mine.
Oh, there you are. Sorry, good. So then, right. Then we don't need to go into this. You know more about it than I do. Right. So they done some very interesting work, which your presentation reminded me of, because a bit like you, they take the precision out of the preferences and put it on the information gain, or they certainly have a temperature there, which is which sort of which gets inverted and wanders around. So it's that perhaps you're doing that because Pedro is a good friend of yours. I see. Sure, good. Well, give him my best wishes if you see him.
Yeah, will do. Yeah, thank you so much for all these references.
Good, right.
David, just from my side, if you do end up going in some of these directions, I'd be happy to chat about it.
Yeah,
I also have some students doing the master thesis now on trying to connect particular processing models to drift diffusion models. So there
yeah,
might
we
be,
should definitely chat.
yeah, but just not that I'm an expert in, well, the HDF I know somewhat well by now, but where I can be helpful, I would love to talk.
Well, you could promote the Julia. If he's written his own Python code, you can try and get him to use Julia to see if he can reproduce it in Julia.
Yeah, so also on the, as you said, Carl, the fitting side, it's something, the software I'm making to make it work with these simulation-based methods has also been very interesting to me. But lots to talk about later. I think the days get...
Before you make us clap, Peter, also Thomas Parr, I think is he's in Oxford as well. David, you're in Oxford, aren't you?
Yes.
Yeah, I think Thomas is applying for a sort of a clinical neurology, academic neurology post, which will give him perhaps 6 months a year research time. So if you reach out to him, he'll have a particular view of these things as they're deployed in neurology. And so he would be another local resource if he gets the job.
Yep.
Then I do think the meeting time is spent, but spent very well, at least from my perspective. Thanks for the presentation, David, and everyone for the discussion and the feedback afterwards. Let us one last time unmute our microphones and give you a round of applause. Thank you all. I will send you the recording, David, and enjoy the rest of the day, everybody.
Thank you, everyone.